How do we find out the definite integral from a to b of x squared dx without finding its antiderivative? Just pretend we haven't learned about Newton-Leibniz formula. Here, of course, we assume a and b are both positive and a is less than b. And we're only going to use the original definition of Riemann integral, using the limit of Riemann sum, where the sum of I from 1 all the way up to n of f of c I times delta xi, limit as the width of the partition approaches 0, p double bar or p modulo represents the length of the biggest small interval in our partition. Here our partition x0, x1, x2 all the way up to xn, and a is denoted as x0 is denoted as a, and xn is denoted as b. Here delta xi is equal to xi minus 1. So I'm going to use the special, first of all, the selection of ci is random and arbitrary, but however I can select eta I. I can select the special point eta I equals the square root of a third of xi squared plus xi times xi minus 1 plus xi minus 1 squared. So the magical number 3 and the weird expression, where did it come from? I'll explain. So the reason I came up with this expression is that using this I can show that eta I is in fact lives inside the interval xi minus 1 to xi. Why? Because first of all, like we assume that a and b are both positive, so that means all of my xi's are all strictly positive. And of course, here is a positive term, there is a positive term. Here I have positive times positive, still positive. So here we have a positive term inside the square root. So this is fine, definitely going to be legal, right? Going to turn out to be a real number. I use a plus square root because eta I will definitely be positive as well. Also, I'm going to show that without the square root, how can I, for example, eta I square, right? This is without the square root. Eta I squared is equal to just 1/3 of this expression is less than, I'm going to replace xi minus 1 with xi, because xi is larger than xi minus 1, right? So this is enlarged. Xi squared plus xi squared. And I'm going to replace this xi minus 1 with xi. It's again enlarged, right? Everything is positive. So plus xi squared. I have 3 times xi squared on top. On the bottom I have 3. They just simply simplify down to just xi squared. So which means, given that both eta I and xi are positive, then I can conclude that eta I is indeed less than xi. Now I'm going to show that eta I squared is larger than third of, I'm going to make it smaller by replacing xi with xi minus 1. Here, xi with xi minus 1. So everything is smaller now. So I have xi minus 1 squared plus xi minus 1 squared plus xi minus 1 squared. That is equal to just xi minus 1 squared, given that both of them are just positive. So it's easily eta I is larger than xi minus 1. So in fact, eta I is not only less than xi, but also larger than xi minus 1, which means eta I really lives inside the interval of xi minus 1 to xi. right? So this is perfectly restricted. Then I can use this fact to estimate the difference of, I'll show right now. So I'm going to rewrite my Riemann sum into, so sigma I from 1 up to n. First of all, I'm going to use the eta I, f of eta I. F of eta I times delta xi. And I'm going to plus f of xi minus f of eta I times delta xi. Right, it's still the same thing. So f eta I delta xi, here is a minus f eta I delta xi. They cancel out. I'm left with f xi delta xi. So still the same Riemann sum. Later I'm going to estimate this sum, show that it is actually approaching 0. And so so regarding this sum, what does that equal to, right? So remember, f is x squared. I'm going to replace x with eta I. Eta I is this. So eta I squared, right? Eta I squared, the square root is gone. So this is equal to I from 1 to n delta x, so f, right, squared, third of, first of all, xi squared plus xi times xi minus 1 plus xi minus 1 squared times delta xi. Delta xi can be written as xi minus xi minus 1. Right, this is my first sum. And as for, I'm going to split up into two sums, plus the sigma of I from 1 to n of f of xi minus f of eta I times delta xi. And this is in fact a formula of difference of cubes. Right? Cubes, difference of, so this is equal, first sum actually equals sigma I from 1 to n xi cube minus xi minus 1 cube. And there is third xi cube minus xi minus 1 cube. Difference of cubes, right? There's a formula. And so later I'm going to analyze this, right? This. Just focus on this sum, right? This sum is now simply can be written as, I'm going to extract the 1/3 out here, right? The I from 1, that is x1 cube minus x0 cube plus x2 cube minus x1 cube plus, maybe just write one more term, x3 cube minus x2 cube all the way up to xn cube minus xn minus 1 cube. Bracket, this is my first sum. So we can just simply cancel out the majority of the terms. x1 cube minus x1 cube, x2 cube minus x2 cube, but x0 minus x0 cube still stays. And according to this pattern, we will eventually So each pair, the pattern is that each pair, one pair, one pair, one pair, each pair, the later term will just be gone, and the first term of the pair will still remain, right? So in other words, the last pair, the later term will just be gone, and the first term of the pair will stay, right? Xn cube and minus x naught cube, they will remain. That is 1/3 of xn cube minus x naught cube. And that is equal to, like I said, I denote xn as b. I denote b as xn, and I denote a as x naught. So that is 1/3 of just b cube minus a cube. So that looks very familiar. So if we, but we pretend we haven't learned the antiderivative or everything. So this is my first sum, right? So now, as long as I can prove that my second sum approaches 0, then we're done, right? So we hope that this will approach 0 as the p modulo, the width of my partition is small enough. In other words, as long as my partition is narrow enough, then if I can show this is small enough, then I'm done. Okay, so now I'm going to show my second sum is small enough when my partition is narrow enough. So first of all, x squared as a function is obviously continuous everywhere over this closed interval AB. Therefore, it's easy for us to draw the conclusion that this function has to be uniformly continuous. Therefore, for any 2 points within this interval, t1, t2, so given any epsilon larger than 0, then I can derive a positive constant. Let's call that so epsilon over b minus a, right? So this is also any given positive constant. Therefore, there exists a delta larger than 0. As long as for any t1, t2 that live inside the interval AB, as long as they're close enough, then their corresponding functional values have to be close enough as well, right? Then f of t1 minus f of t2 will also be close enough. Or maybe smaller than epsilon over b minus a, right? As for this epsilon over b minus a, derived from any given arbitrary positive number. Once given, we fix it, right? And I really found, right? So this delta is what we found using the property of a uniformly continuous function. So this has to hold true. Therefore, is as long as I make sure that Xi and eta I are close enough, right? So first of all, 2 points have to be close enough. Can I make sure Xi and eta I are close enough? I think so. Why? Because first of all, previously I've proven that eta I actually lives inside the interval xi minus 1 xi. And also Xi also given to be, according to our original definition, Xi also lives inside the interval xi minus 1 xi. Therefore, their difference. So Xi minus eta I, their distance has to be no larger than the length of the interval, right? The length of the interval is xi minus 1, denoted as delta xi. Right? Those 2 points both live inside the interval. And this interval is no larger than the maximum, than p modulo, right? Maximum value, the longest interval out of all the small intervals, right? So no larger than p modulo, right? So in order to make sure that those 2 points are close enough, I just have to make sure that p modulo is small enough. How small? Smaller than delta. Of course, this is totally achievable, right? Because delta is what we found using the property of uniform continuity, right? The delta definitely exists. Using this fixed delta, we just let p modulo be small enough, right? So this is even smaller than p modulo. Therefore, this is now made sure to be small enough. So, according to this property, as long as those 2 points inside this interval are close enough, then their corresponding functional values will be close enough, right? So we made sure that those 2 points are not only within this interval, but also close enough. Therefore, their corresponding functional value will also be close enough, right? Therefore, the absolute value of f of Xi I minus f of eta I, right, will also be small enough, smaller than this one, right? Epsilon over b minus a, small enough. So therefore, I wanted to show that this quantity is small enough, right? So in other words, if I just add an absolute value here and use the triangle inequality to make it larger by moving the absolute value inside here, right, then further loosen the inequality using this amount, right? So that means the absolute value of this amount can be shown to be smaller than epsilon, right? So already smaller than smaller than I from 1 to n epsilon over b minus a times, don't forget there is a delta xi, right? So absolute value, take the absolute value inside. Inside here, absolute value replaced with this positive constant. And take that positive constant outside. Times the sum of delta xi from 1 to n. So what is that? That is b minus a, right? Because delta xi is the length of each small interval. What's the sum of the length of each of the small interval? Obviously, they add up to the length of the interval AB, b minus a, right? So b minus a, b minus a cancel out, equal to epsilon, right? So really, this amount is really small enough. So I've really shown that when the width p modulo is small enough, in other words, when my partition is narrow enough, right? In other words, the largest interval of my small intervals of my partition is small enough, then my Riemann sum, right, same thing, is actually close enough to this value, because this value already shown to be close enough to 0, or small enough. Therefore, my Riemann sum really is close enough to this value, right? That is its limit. In a future video, I will show how to find out the definite integral from a to b of x to the power of m being any positive integer. It doesn't have maybe 3, 4, 5, using a number of different ways.